Welcome to this episode of Eureka. We are having a very wonderful, very interesting guest today in this show today. Jhansi. The moment we hear this word, the first thing that comes to our mind is the icon of Jhansi, Jhansi Rani. There is another icon that we all need to celebrate, that is our guest today, Dr. Archana Sharma from CERN, which is world's one of the biggest laboratory experimental physics institution in Europe. Before we continue this conversation, let's take a quick look at her brief profile and continue this conversation. Keep watching Eureka.
There are many mysteries about the universe which are still unanswered. And to decode such mysteries, many physicists have extensively worked. It is where Dr. Archana Sharma, who made a significant scientific contribution to international repute. Presently, Dr. Archana Sharma is a senior staff scientist at the CERN laboratory in Geneva, Switzerland. She has been active in the field since 1989, mainly working on instrumentation, especially gaseous detectors. She is the pioneer of simulations and experimentation on wire chambers, resistive plate chambers, and micro-pattern gaseous detectors over last 3 decades. Following a graduate degree in nuclear physics from BHU Varanasi in India, Archana received her particle physics PhD from Delhi University in 1989. Followed by an instrumentation for high energy physics, Doctor in Science from the University of Geneva in 1996. She is an internationally recognized expert for her experimental work on gaseous detectors for research in high energy physics. Dr. Archana has worked on several CERN experiments, both on R&D, being involved in designing and prototyping, and on running laboratories for construction, installation, and commissioning of large-scale gaseous detectors. She is the founder and leader of CNS, a GEM collaboration for exploiting one of the most sensitive detectors for triggering and tracking in the CMS experiment at LHC with the highest discovery potential. Dr. Archana pioneered the development of micro-pattern detectors. Her publications, review articles and book, a special volume on instrumentation on particle physics edited by her, are widely referred to and cited. Since 2001, Professor Sharma has led the construction of gaseous detectors and is well known for incessantly mentoring students into professionals. Dr. Archana has got many recognitions and also has been very actively facilitating knowledge exchange and capacity building in the science and technology sector.
Thank you for being in the show. I mean, it's a very interesting opportunity even for me. I mean, in a sense, if one has to say that CERN is like the Mecca of science, or Vatican of science, or maybe even Varanasi of science, one can say so, right? What is this CERN? What does it do actually?
CERN is actually an acronym, a French acronym, Centre Européen pour la Recherche Nucléaire. So it's like nuclear particle physics research for the European nations. Essentially, after the World War II, many of the eminent scientists of Europe were running away to United States for better opportunities. So to keep them back home, this kind of a center of excellence was created, just like the United Nations or other bodies like the United Nations. And then those scientists had a big foresight of creating a nucleus, attracting people, and this was in 1954, and slowly it grew to where we are today. Today we are more than 15,000 people who work there, from all over the world, in fact. So it's not only European anymore, it's more like the International Laboratory of Particle Physics.
Okay, so it started originally as a European laboratory, but has now kind of bloomed into a international institution where how many countries, people from how many countries are actually part of this institution now?
I think I wouldn't be wrong in saying that there are more than 150 countries represented at CERN.
Okay, that's a really huge number. It means that almost all the world, I mean something like a United Nations or a WHO,
Absolutely.
the whole world is involved.
It's collaborating.
What does this institution do? I mean, what is the question fundamentally the institution wants to address?
So, human curiosity has been the driving force for all research and then innovation and then society and so on. So, this kind of curiosity driven research is what CERN masters and does. And it's really looking at the mysteries of the universe.
Okay.
Where did we come from? Where did all the antimatter go? Because after the Big Bang, there should have been equal amounts of matter and antimatter.
Okay.
But we are here. So it means that matter was not completely annihilated by the antimatter. So there was an excess of matter. But why? Why does matter and antimatter behave differently? Are there other universes out there?
Okay.
Or we are the only inhabitants of this universe, one universe, that's why it's multiverse and so on. Are there other dimensions? When an ant on a table lives on the table, she can see only 2 dimensions.
Yeah, it can just either go forward, backward or left or right. But whereas a fly can go forward, backward, left or right or up or down. So the fly can actually experience the 3 dimension, right? Yeah, so what do you mean by then when you say that many dimensions?
So Einstein taught us that there is a 4th dimension called time.
Okay.
So it's amazing that such a simple concept that the space and time is one. We meet yesterday, it's another space time. Today is another space time, and we cannot conform this in any other way than having a 4th dimension.
Okay.
Similarly, there could be other dimensions.
Which we are not feeling or which we are not able to touch. I mean, it's not it's not possible to us in a sense, right?
And if we put together all the knowledge that we have today from astronomy, from cosmology, from particle physics, what we gather is that we can understand only or explain only 5% of the visible universe.
Okay.
Where is the 95%? Are black holes there? Yes, they are.
But what does this black hole consist? It's still a mystery.
It's still a mystery. So there is a theory, and all physicists know that when we don't understand something, we call it dark.
Yeah.
So dark matter or dark energy, because we don't know what it is. So if we find a candidate of dark matter in our experiments, that's going to win us the next Nobel Prize.
That's very interesting. But there is a bit of confusion for me. The CERN is a particle accelerator. Basically what you are doing is that you are taking particles, make it go round really fast and collide head on. It's like, for example, if there are let's say 2 cars, I don't know what is inside it. I make them collide, make them break it into parts, and then see that, oh, there is a steering wheel, there is a engine, there is a carburetor, that kind of stuff.
Correct.
I can understand when you say that through these experiments, we will find out what is inside atom, what is inside proton, what is inside quark. I can understand that. Or quark, like some other new particle is there, I can understand. You talked about we will also do experiment on, or this experiment will reveal us knowledge about multiverse. For that we need telescopes, right? Or are we wrong somewhere?
No, we are not wrong somewhere. Tell me something. Do you believe in dinosaurs?
Yeah.
Why? Have you seen one?
No, but there are indirect evidences. Like, for example, footprints of dinosaurs are there.
So there are signatures of what you have seen.
You can see bones in some places. You can see full bones in some places. Now, bones of different kind. If I put them together, it's a full bone. So I can see that it was there all over the world.
Yeah. So you have not seen a dinosaur, but you believe because you have seen the signatures and footprints and so on. So similarly, in the collisions, we create particles that existed at the time of the Big Bang, but do not exist anymore. So with the energy available for the collisions, like you explained the collisions very nicely, in this 27 kilometers, we are shooting protons on one direction and we are shooting protons in another direction. And when they collide, there is energy available to create particles that do not exist anymore, but existed at the time of the Big Bang. So we are creating a mini Big Bang.
Okay, that's very interesting. This is where I want to ask you another question. When CERN become like a household name, not just only in India, all over the world, that was when the big announcement came. You know what popularly is called as God particle. We know that it has nothing to do with God. It is just a particle which explains why matter acquires mass. Okay, that's there. That's interesting. After that, we got an announcement that CERN is shut down. We are now going for an upgrade. If from the earlier experiment itself we can know what exactly existed at the time of Big Bang, why do we need update?
So in the years of the 90s, there was a predecessor of the present machine that was operational for 10-11 years. And we tried our best to find the Higgs boson, the God particle, but we did not find it because we were at the cusp of the energy. And we just did not have enough energy to create the Higgs boson. Simply because the Higgs boson is rather heavy particle. You know, if you have to make a big laddu, you need more than enough the dough to make the laddu, right? So similarly, we need more energy to create the Higgs boson. And that energy was just available when we restarted the LHC. So once we have now created the Higgs boson, there are many theories which tell us, is it the only boson? Or there could be other similar particles, sister particles, brother particles.
You know, something like, for example, there are sister particles to electron, right?
Bilkul. So we need to then understand further. There are several theories. There are partners like supersymmetry theories. So we might be able to find SUSY particles or dark matter candidates and even study the Higgs boson. We have just created a new baby, let's put it this way. We have no idea how it behaves. And maybe baby is not the right analogy. If it's like an elephant that we have just found.
It's an unknown animal.
Unknown animal. So we have to check every bit. So it's like finding
the first dinosaur bone. We know that something existed, but we don't have the full picture.
Absolutely, yes. So we have to study it very carefully so that then we know how it decays, how it behaves, how it interacts and so on. So that's the study we need to do now. And then we have shut down to upgrade the accelerator and to upgrade the experiment, which is our microscope through which we are looking at these collisions.
Very interesting, very interesting. This is where we will take a very short break. Keep watching Eureka. After the break, we are going to discuss about what is her work in this huge team effort. Keep watching Eureka. We'll take a very short break. Welcome back to Eureka, and we are having a very interesting, very informative conversation with Dr. Archana Sharma. She is a scientist with CERN. And by the way, you know, she was almost about to finish her PhD. Then the university changed the rule. And she had to give an exam in French. She slogged for 6 months, studied French, gave that exam, and passed with flying colors. And today, she is one of the foremost researchers in the area of fundamental particle physics. It's a very, very interesting story. Just recollect that story. I mean, how did you feel that time when that new, regulation came in the university that you have to pass an exam, when you were almost about to submit your PhD and get your doctorate?
Right, it was quite a blow, I would say, because I had undertaken a second PhD for the reasons that, I needed to do a lot of instrumentation work, and I felt intimidated by all the instruments and so on. So this was a great, let's say, move to learn. However, 2-3 years into the PhD, right in the middle of the PhD, I was told that I have to take this exam. Now, the medium of education in Switzerland is in French, in the University of Geneva. and this was nearly, I think, 15-20 years ago.
Okay.
So in '96 I got my second PhD.
Okay.
So you can imagine, it was frightening that how will I be able to pass this examination, you know. So I went around trying to see how can I do this, you know, nobody is going to listen to me. And you know, rules are rules. It's not that you can stretch them and you say, no, just for me make an exception or something like that. So I did an Indian jugaad. I found a tuition for myself.
Okay.
I went looking for somebody who could help me, and I found a very nice Italian postdoc who helped me, and he gave me classes. He sort of explained to me how the content of this examination.
Okay.
Plus, I of course took a lot of French lessons with my colleagues who helped me a lot, and eventually managed to get through the exam. So
that should have been a really tough time, right? I mean, thinking almost you are going to end, and then suddenly this
that's
change.
true.
Let me ask you a different question. I mean, you were saying that there was an earlier version of CERN, then an upgraded version, which is where actually we were able to detect a Higgs boson, and a new version that is coming up. You were there from the pre-version, and also the version where the Higgs boson was discovered, and then the new version. So let me ask this as a 3 question. What was your contribution in the first, that is before the Higgs boson integration? Yeah.
So very initially, of course, it was a learning phase for me. So I went completely into somersaulting into learning everything, how I can be useful, which will be my field, because initially you are exposed to so many things, and you have to find your interest first of all. And when you find your interest, then you have to ensure that you will be able to sustain that interest. So I enrolled myself into an R&D program.
Okay.
And for the first 10 years of my professional life, I have been working on R&D, on small detectors, which are actually used now. So that was a very good training ground for me.
Okay, okay. That was your first time?
First 10 years,
okay.
yes.
So the upgrade, which actually detected the Higgs boson, okay, in that, what was your contribution?
So I was part of building large detectors, very large detectors, which means of the order of thousands of meters squared.
Thousands of meters squared?
Thousands of meters squared of detectors, each being of the order of 2 meters squared by a meter squared.
Okay, okay.
So building small detectors in the 90s, and then in the years 2000 and so on, I built very large detectors, and I was coordinating the construction, the assembly, the quality control, the qualification, installation, commissioning, and eventually data taking from those detectors.
What is this instrument was called as?
Those detectors were called the RPC detectors.
Okay, RPC detectors, fine. So now coming to the third, the upgrade right now happening. I'm sure you also have some role in it, right? I mean, you should be contributing a significant part. What is it that you are doing in this?
So while in the 90s, I participated very actively and also contributed to the development of a new generation of detectors that is called the gas electron multiplier, the GEM.
Okay.
That was in
gas
the 90s.
Electron Multiplier.
G.
GEM. So you are producing GEMs.
G. So you know, that was a little dream and a little how can I say, hope that maybe later on in life I'll get an opportunity.
Can you in simple terms explain what is this GEM?
So when a particle goes through a detector, and a detector is nothing more than a microscope or a camera taking photos of the collisions that are happening in the accelerator, we would like to take pictures 40 million times a second. So these are very highly performing detectors that you need to be able to sustain, to take pictures in that speed, plus make decisions on keeping the data or throwing away the data.
Okay.
So the gas electron multiplier is a very high rate capable detector, and it works on the principle of multiplying an electron that can pass through a hole that has been created. The hole is in a capsule.
Well, okay, let's understand this. When you say the GEM instrument, in a simple term, explain how will the GEM instrument is constructed. It will be a gas tube?
No, it's a foil, flat foil tube. It's a planar detector. So if you take a tabletop kind of a size, and I have a planar foil of Kapton, and I copper clad it on both sides, and I pierce it chemically by many holes, identical holes of course, And if I apply a voltage across this foil, then in each hole I have a very high electric field.
Okay, there is a high electric field in each hole, and you have created millions of holes.
Millions of holes,
yeah,
right?
Okay, fine. That is there.
G.
Yeah. Then
when your particle will go through the detector, because this foil is not just hanging in the air, it is in a delimited inside a gas volume.
Okay, there is a gas, and then you are sealing that gas.
You are making a package of a detector, like a sandwich, where you have, a detection electrode, your 3 gem foils, and a drift electrode, which actually contains the gas. So you have the drift and the detection electrode. And these 3 foils are identical. Each foil acts as a multiplier. When your particle goes through in the gas, it liberates electrons and ions.
That's what is happening in any tube light, right? That's exactly
everywhere.
What is happening.
Exactly.
Okay, fine.
But in the tube light, you get photons, and in the gas, you have electrons and ions. So these electrons then are accelerated towards the holes, and inside the holes, they find a very high field where they multiply. So from 1 electron, if we get 20 or 30 in the hole, and if we have 3 of them in tandem, 3 foils in tandem, we will get from 1 electron up to 10,000 electrons.
Okay, so you are multiplying it like from 1 to 10,000.
That's right.
So in a loudspeaker, for example, we will multiply 5 times, we will multiply 10 times our voice, but whereas you are doing it about 10,000 times, because you want to detect even weak signals. That's a thing. This upgrade is actually will be able to detect even weakest signal, which you are not able to capture in the earlier. Am I right? I mean, is that?
You are right.
Huh?
Not only the weakest, but also in time you will be able to take 2,000 signals in 1 second.
Okay, so it also can detect more. Rate will be much more.
The rate capability is very high.
So this gem is going to be part of this upgrade. Is that so? Okay, that's very interesting. You, as somebody who is working in CERN for quite a long time, have been participating in this and then developing this detector. Now it's going to be part of that. How much Indian institutions are involved in it?
There are many Indian institutions that are involved at CERN from many decades actually. And very recently there is the associate membership that was signed in 2017. So this is being ramped up as well. And there have been significant contributions in many experiments, in the accelerator, in the IT department, and all other grounds where CERN is working.
Okay, very, very interesting. Let me ask you this question. The time that you were in schools, 1970s, if you look at most of the students, if they have some passion for doing something in their life, usually it will be like, oh, I have to become an engineer, I have to become a doctor, right? That's a kind of general attitude. Not many people would have had a passion that, oh, I want to do research. How did you get into this? What spurred you into research?
Well, research came a bit later, I would say, but in my school I had a fantastic physics teacher, first of all, so she was really my favorite teacher, so favorite subject, of course. And then it happened one day in class, she just asked the class, so how would you reset a thermometer?
Okay.
And since you have a magnetic ball bearing there, which you could reset, use a magnet to reset it, I got an idea from somewhere that we can reset it with a magnet.
Okay.
And she was very surprised, first of all, because those were not the days when kids used to play with magnets and so on. And she was so happy that she encouraged me a lot. And I thought maybe I know something, and maybe I can take up physics in my future days.
That's how you entered into physics, and that's where you are right now. Okay, yeah, okay. So when you first went to CERN and started learning, for example, simulation, you were so excited. So, I mean, it was a new tool, right? So, what is that incident that happened in your life?
Well, that was a funny incident, and this happened with George Sharpak, who was a later Nobel laureate in 1992. And I had the good fortune of working with him. When I learned simulations for the first time on how we can work on avalanches and gas detectors and so on, I first learned how to make a plot. It was a very basic thing, of course, but I was excited to see on my computer that from my data I can make a plot, which I had learnt before only through a lot of rigor, but this was really automatic. You press a button and you get a plot after all the simulations that you've done. So I went and I immediately shared this with George Sharpak, and I was a young student, excited, and he says, fine, now you've got the screwdriver, go and make the instrument. Okay. This is just a screwdriver.
Yeah, that's a very interesting point. I mean, one should always try to look for the next step rather than just be happy with what you've done. That's one of the important thing of, you used a word in the beginning that CERN is essentially working on curiosity-driven science. Is it an esoteric institution which is answering only esoteric question, or is there any social use of such kind of research?
So the first thing I would say is that I'm sure you know the words www, the letters www. Yeah. And you do know that this came out. In fact, I contacted you through that. Okay. So, did we know in 1990, when the first web page was created at CERN, that what a $1 trillion revolution will come about from the www? And you mean to say that www was created at CERN? Was created at CERN. Very interesting. When you walk through the airport, security, there is all this detectors in the end of the day that detect heavy metals or drugs or other things that people may be hiding. Those detectors are made by the laboratory physicists. Oh, so it's something very similar to the detectors that you are constructing. Very interesting. Okay, then you go to the hospital, you do an MRI. You have treatments for various cancers that use accelerators. Imaging for diagnostics also use detectors and algorithms that are developed at CERN. So at CERN we have so many technologies that you will find everywhere in your daily life, and you cannot separate daily life and curiosity in the end of the day. Okay. Yeah. I mean, let me give you another example. We all know about relativity and Einstein. Yeah. And of course, then when you look at where will you use it? Yeah, exactly. That's perhaps a lot of people have this. It's a very interesting, something like a science fiction, but it's only a fiction. That's what most people think. Yeah. But today, everyone uses a GPS, which is in practically every car that we sit in today. And if it were not for relativity and the corrections for relativity, we would be off by 5 meters every second. Off by 5 meters every second? So this is like the corrections and the equations that go behind making an instrument like the GPS operational. Very, very interesting. So with this, I want to ask a question, which perhaps should be the last because we don't have much time in the show. Many people think that a country like India should not be spending on fundamental sciences. We should spend on applied sciences. There are a lot of poor people, there are people with sickness, there are lots of other social challenges. We should spend on it or not. Why do you go to Chandrayaan or why do you do Mangalyaan when people are suffering in the streets? That's a kind of one opinion which is there. As a person who has worked in this field for quite a long time, what's your take on this question? So my take is as follows, that we have been trying to do technology and R&D as we see in the West. However, we are not doing enough investment in R&D. So the West has gone through similar crises, but 100 years ago. When you want to buy an iPhone today, you will not buy iPhone 5 or iPhone 6. You will run for the iPhone 10 or 11. So this is called accelerated advancement, isn't it? So we should profit from the experiences of the West and in India go for accelerated advancement. In India, we do have all these issues, but let's look at the solutions that already exist. And R&D investment is a measure of the GDP of a country. If you look at Germany or the UK or France or Italy, you will see how much of a fraction of their GDP do they invest in R&D and how much they have been investing in the past. So if we follow that model and follow the iPhone model, which means that today we should go for the fast track development, I would say.
So you are saying that we should be actually not spending less, but more.
Absolutely.
Only then you will really have, if you want to solve the problems, the
impact.
technology and other tools that you need to solve it, right?
Absolutely.
Very, very interesting and very important point. And with this, we need to end this conversation and this show for want of time. Keep watching Eureka. We'll come back with another interesting episode next week, same time.